Alright, so in this particular problem, we have a stack box system here. It says two boxes stacked on top of the other can move without friction on a horizontal surface as shown below. And this is the surface between the two boxes. It's rough, however, with the coefficient of friction mu, which is equal to 0.18. Okay, so here's box A. Box A rests on top of a smooth surface. However, on top of box A, there is box B, but there is friction between box A and box B, and the coefficient of friction is given to us. Alright, so let's go ahead and do A and B. It says A here, if a constant force of 200 newtons is applied to box A, so here's a person, this person is going to push with a force of 200 newtons, and it says what is the acceleration of box A. Okay, so let's go ahead and do this. In order to do the acceleration of box A, let's set up Newton's second law for box A. So here I have net force of F on box A, which is equal to mass A times its horizontal acceleration. But before you do this, you should definitely draw out your forces. Here, my purple arrow represents the force being applied onto box A, which is 200 newtons. And then I'm also going to identify the frictional forces that exist between B and A. So here is the frictional force that exerts between B and A. I have an arrow pointing leftward, which I will just call F of friction, and then I have an arrow pointing rightward. Same magnitude, just different direction, because this is a contact force. So in physics, a contact force would have two opposing arrows. However, the length of the arrow needs to be the same. So the magnitude has to be the same, but the arrow serves a different purpose, which is based on the perspective of A or B that you're assessing. Okay. All right. So therefore, both these blue arrows are labeled as frict. One points left, one points right. So let's go ahead and do part A. In order to do the net force for box A correctly, you would have to look at box A. So please watch what I'm circling. I'm circling box A. However, the motion of box A is generated by this applied force of 200, which is pointing to the right. However, placing a box on top of box A would cause it to slow down. So in this case, I need to use this arrow that's pointing leftward for F frict. Okay, so for box A, I have two vectors, one pointing to the right, which is F of 200, and then the arrow pointing to the left. Again, placing a box on top of the bottom box would only produce a slow acceleration. That would imply that you're acting against the box's motion. So therefore, you need to pick an arrow that's pointing leftward in the opposite direction, not rightward. Alright, so therefore, here I can replace F of fric. By definition, F of friction is just the coefficient of friction times F of n. But I don't know what F of n is, therefore I need to go ahead and look at this particular system. The frictional force exists between box B and box A, which would suggest that the surface in which the box B is sitting on is the top of box A. So the weight of box B is pushing down on box A, which is called F of GB. However, as box B is pushing down on box A, it generates a counterforce, a contact force from box B, or excuse me, from box A onto B, which we call the normal force. Okay. These two arrows are opposite and equal in magnitude, so therefore we can replace F of n with F of GB because they are equal in magnitude. So here I just carry my work down. F minus mu k, or excuse me, minus mu, because I don't know if it's moving or not moving, so I can't really use subscript k or s. So I have F minus mu times Fn, but Fn in this particular problem is just the mass of B times the acceleration due to gravity. Okay. Now we can just substitute values in. F in the diagram is 200 newtons. The coefficient of friction is 0.18. Mass B is 25, and then the acceleration due to gravity is 9.8. It's important that you plug in a positive value here because the negative sign has already been taken care of for you. Okay, so be careful when you get to plug in G. In my work, I have already accounted for the negative sign, so it's important that you just plug in 9.8, not negative 9.8. On the right side, mass A is just 75 kilograms, and then the only thing that's unknown here is AX. Okay, so if we simplify this on our calculator, on the left side, you would get about 155.9. And then on the right side stays the same. To solve for AX, we just divide both sides by 75, so 155.9 divided by 75 kilograms would be 2.08 meters per second squared. Okay, so the acceleration in this case would just be 2.08 meters per second square. But if you read part A, it says find the acceleration. I didn't use the word magnitude. So to be proper, I would say positive 2.08 meters per second square, or 2.08 meters per second square east in this particular diagram. All right, let's do the acceleration for part B. It says, what is the acceleration at the top box B? So in order to do the physics for part, or the top box B, we would just set up Newton's second law for the top block, or box in this case. It would be net force of box B, which is equal to mass B times acceleration. Okay, but the only force that's causing box B to move is this particular friction force here. So this particular problem, even though you're pushing box A, box B will either move with the system for the whole entire time, or it moves for a little bit and then eventually slides off, and that is something we have to assess here. Okay, so, but at least you know they'll move together for a little bit of time. How much time, I don't know, because the length of the box is not given, but I do know that if they move together, it'll be for the whole time. But if the acceleration is not the same, box B will eventually fall off. How much time, again, I don't know. The problem would have to provide you with enough information for you to figure that out. So the only force acting on the top block is the frictional force between the two surfaces. So I'm going to use this right arrow. So box B can only move rightward. In this particular case, how fast is it moving rightward? I don't know, but I need to use this particular vector pointing to the right. Therefore, net force for FB would only be one term. It is the force of friction between the two surfaces, box A and box B, that's going to cause block B to move. But by definition, the force of friction is mu times F of n. But we already know that from our previous work in part A. The force of friction is simply mu times F of n, but the F of n here is contributed by mb, because this is now your surface. Watch where my cursor is tracing back and forth. The force of friction exerts between box A and box B. So therefore, the top of box B is my surface. So if I need my normal force, I would just count from the surface up. So therefore, the only force that's pushing down on it is the weight of box B. So therefore, a normal force is contributed to the weight of box B, which is 25 kilograms. Okay. But as you can see here, mb cancels out on both sides because it appears on both sides. And then to find the acceleration, we would simply take the coefficient of friction times 9.8. So if we punch that in, we should get a value of about 1.764 meters per second squared. So right away, hopefully you can see that the value for box A is 2.08, but the value for box B is only 1.764. So right away, I can tell that box B accelerates slower. Well, if it accelerates slower, then it will eventually fall off or fall behind relative to box A. Okay, so our conclusion here tells us that box A will accelerate faster, box B accelerates slower. If that is the case, box B will eventually slips off on top of box A. Okay, but to find the value for acceleration of box B, there it is, 1.64, and again, 1.764 east or positive 1.764 would be acceptable. However, this particular site is to show you there's another way to assess whether the system moves together or not. So please keep up. Okay, I said here, let's assume that the box do move together. From our previous work, we know that they don't move together because the acceleration from box A was faster than the acceleration from box B. But in this strategy, I'm just going to assume, what if they were to move together? Okay. If they were to move together, then I would set up the system. I would have the net force of the system equal to the total mass of the system times the acceleration. Because they move together, I want to just group everything as one. Well, what is causing the system to move? It would be the applied force here of 200. But if they do move together, they would have the same acceleration. Okay, so if I'm looking at this particular system, if they do move together, the contact forces between the two boxes would cancel out because it moves as one. And if I'm looking at the system, then therefore the contact forces will always cancel out. So with this assumption, I can say that, well, I can find the acceleration. To find the acceleration in the system, I can just simply divide both sides by m total. Well, F is 200 because that's what is being applied to the system. The total mass of the system is 100 kilograms because 75 plus 25 is 100. So and if you simplify that, you should get a value of 2 meters per second squared. So if you were to push the system, and if they were to accelerate at the same rate, the rate of acceleration would be 2 meters per second squared. Well, what are you going to do with this? Well, in order for the top box to move at a rate of 2 meters per second squared, it needs a certain amount of coefficient of friction. Okay. So here I want to look at box B. Well, I can set up the net force of box B. The only force acting on box B is once again the frictional force that exists between B and A. These blue arrows here. What's causing box B to move once again is this blue arrow to the right. Therefore, I'm just gonna go ahead and introduce F of fric. There is only one force acting on box B, which is the force of friction between A and B. Well, this work is for MB, so on the right side you see MB. And if I expand F of fric again, we get the coefficient times the normal force. But the normal force, once again, can be broken into MB times G, because the top of box A is now our surface. So therefore, to find F of n, you would just count only what's sitting on top of that surface, which in this case is the 25 kilograms, which is mass B. But you notice here, MB cancels out again, okay, because it appears on both sides. So to find the acceleration, or excuse me, to find the coefficient needed in order to accelerate at 2 meters per second square would be 0.204. So here I plugged in AX, assuming they move together, the acceleration would be 2. G is 9.8. So what is needed in order for the top box and the bottom box to move together? The coefficient of friction that's needed is 0.204. But may I remind you, in the diagram here, the coefficient is only given as 0.18. So therefore, hopefully you're keeping up. With this conclusion, I made a statement here. Okay. In order for the system to accelerate together at a rate of 2 meters per second squared, the coefficient of friction needed is 0.204. However, the diagram only gives you 0.18, which is less than what you need. So by knowing that, I can make a conclusion that the top box cannot keep up and eventually falls off. You need 0.204 to keep up, but you're not given 0.204, you're given less than that, which is 0.18. So using deduction, I can say that the force of friction that exists between the two surfaces is not sufficient for the top block, in this case block B, to keep up. Okay, I hope that helps. Stay nerdy, don't be whack.